In this lecture, we are going to see some Bayesian way of thinking, but only with respect to the events. The real Bayes inference will come later, but some of these things with Bayes formula with events and Bayesian reasoning with events is going to be sort of instructive for later. We could be interested in not probability of A and probability of A given hypothesis, but we may be interested in probability of hypothesis given that A happened or did not happen. So that is essentially trying to update the probability of hypothesis in the light what happened to event A. By total probability, we know and we calculated probability of A. That was the weighted average of conditional probabilities where the weights were probabilities of hypothesis. But the probability of hypothesis given A is by definition probability of conditional probability. And this is the probability of intersection divided by probability of event that you are conditioning upon, in this case probability of A. And if you represent the probability of intersection as the product of probabilities in which you use A conditional to HI, you get something which is called Bayes formula. What happens here is the following. You know the probability of hypothesis before the event. Then event A happened. So you know probability, event A happened, and then you update your probability after A happened. So the first one is called prior probability, a priori probability. Probability of event of hypothesis HI before A happened, and that's why it is called prior. The second one is the posterior probability. It is probability of hypothesis HI after event A happened, after we observe what happened to event A. That is the basis for Bayesian learning. We start with Bayes, with prior probability, and we go to the posterior probability. And this posterior probability is essentially probability of A given HI over probability of A. Sometimes this quantity is called Bayes factor times the probability of HI. So this is Bayes formula. Probability of hypothesis given event A is probability of A given hypothesis times probability of hypothesis divided by probability of A. So what is the learning here? Prior to experiment that event A could occur, it occurs or not, we believe that probability of hypothesis is P of H without information about A. But after the experiment is conducted and we observed what happened with event A, we update the probability of hypothesis to probability of hypothesis given A, and that is Bayes formula. Now this is simply a manipulation with events, and you can easily just go through the algebra and prove this. Unfortunately, these days, if you want to be famous and to have some formula named after you, you have to work much, much harder. These formulas are taken in the Middle Ages. They are very simple. Now it's a different situation. You have to work much harder to become famous. So let's take a look at our manufacturing Bayes example. Remember what we had in the total probability. We had these three machines. We know that an item was produced only on these three machines, and we know probabilities of hypothesis because these were production capacities of these machines. It was 30%, 50%, and 20% for machines 1, 2, and 3. And we knew also the conditional probabilities of item being conforming depending on the machine. We found the probability of randomly selected item conforming as total probability. Now imagine the following scenario. You selected the item at random and you found that item conforming. And then you ask question, what is now the probability that it was produced on machine 1? Before you did sampling, it was 30%. But now you took the item, observed that it was conforming, and the question is, what is the probability that it was produced on machine 1? That is Bayes formula. So prior to selection, it is 30%, but then you used Bayes formula. This is the probability of conforming on machine 1. This was the probability of hypothesis H1, and this probability was found as total probability. So when you do the algebra, you get that the probability of item produced on the first machine, given that it is conforming, is a little bit less than 30%, 29.65%. Let's continue with bridge circuit. Remember this bridge circuit in which we used total probability formula to find the probability that circuit is working by conditioning on this element A5, and this element working or failing was producing two hypotheses, H1 and H2. Probability of H1, A5 working was 0.6. Now we are interested in probability of H1 given the fact that the system, the circuit, is working. And simply by Bayes' formula, you plug in the probability that you calculated in total probability in the denominator, and that was the probability of working if the element A5 was working, and this is probability that element A5 is working, and when you do calculation, you end up with 61.59%. So probability that at that item element A5 was working if the system was found to be operational increased from 60%, which is prior probability, to 61.59%, which is the posterior probability. So let's then take a look at one very interesting example. It is two-headed coin, in which the scenario looks like this. You have a big box, and in this big box there are capital N coins. All but one are fair, but one is two-headed. It has head on both sides. You could buy such coin in Spencer stores. It was costing you a few bucks, and then you will flip this coin and amuse your friends that heads is showing up every single time. But this coin is on touch, and by looking at it, indistinguishable from other coins. So when you put this in the box and randomly select one coin, there is no way for you to tell by touching coins which one is fair and which one is two-headed. So you select one coin from the box at random, and without looking which coin it was, you flip it k times. Now all k times that you flip that coin, it came heads up. And the question is, what is the probability that the two-headed coin was selected? Now that is Bayes' formula. Why this is Bayes' formula? The Bayes' formula is because you know exactly what is the probability of hypothesis H1 that fair coin is selected before you start experiment. That is 1 out of capital N. 1 is two-headed, total N coins, 1 over N. But then you conduct the experiment and you see that heads show up k times in a row. And then after some number k heads in a row, you ask yourself, what is the probability that I selected two-headed coin? So let's take a look at the algebra. I set two hypotheses. H1 is that coin is fair, and H2 that coin is two-headed. Probability of H1 is n minus 1 over n. All but one are fair, and probability of H2 that coin is two-headed is 1 out of n. Now let's take a look at the probability of k heads in a row if you have fair coin. It is 1/2 in the first flip. The coin has no memory. The second flip is independent. So it is 1/2 in the second flip, 1/2 in the third, so on and so forth, 1/2 in the kth flip. So probability that coin will fall heads up k times in a row, if it is fair, is 1 over 2 to the k, or 1/2 to the kth power. What is probability of event A if you select it, if hypothesis H2 is true? H2 is that coin is two-headed, and probability that it will fall heads up is 1 for any k. So that is 1 easily. In using Bayes' formula, you will need total probability. You will need probability of A. For randomly selected coin from the box, what is the probability that it will fall k times heads up? Well, this is total probability. It is n minus 1 over n, which is probability of hypothesis H1, times 1 over 2 to the k, which is probability of A given H1, plus 1 over n, which is probability of hypothesis H2 times 1. And when you do this algebra, you get in the numerator n minus 1 plus 2 to the k, and denominator 2 to the k times n. Now, the Bayes formula. You are interested in probability of H2 given A. Probability that you selected two-headed coin if it came heads up k times in a row? Well, by that one, you take, this is probability of H2, this is probability of A given H2, and you plug in this in the Bayes formula on the top. On the bottom is probability of A. And when you do algebra, you end up with result like this. So probability of H2, which is 1 over n, got changed to this number if you observe k heads in a row. Now, let's take a look with some specific numbers. Let's suppose that you have 1 million coins, huge number of coins in the box. All of them are fair but one. One is two-headed. If you flip the coin and it came 20 times in a row heads up, then the posterior probability of hypothesis H2 increased from 1 over million to more than 50%. But imagine that instead of 20, you got experiment, you flip the coin 40 times, and in all of these 40 times, you got the heads up. Then the probability of hypothesis H2 prior, 1 over million, got improved to probability of almost sure event. So after seeing 40 heads in a row, you can almost bet your life that you will get that you selected two-headed coin, even though there is only one two-headed out of million in the box. That is learning property of Bayes rule. After the experiment, you learn about prior hypothesis. So in summary, we saw the Bayes formula and Bayes learning in the domain of events. We saw application of the Bayes formula for the manufacturing example, and we saw application in the example with two-headed coin and the bridge circuit. And now I'm going to show you two examples actually repeat these examples using the software. One is going to be using Winbugs that we discussed briefly, and second is going to be using the Octave or MATLAB, whatever is available to you. Thank you.